Okay, I'm going to do a few more examples of steady state errors and other performance measures, especially in the case of unity feedback systems. And this will wrap up um, steady state error stuff, and also it'll wrap up my module 4, which is time domain analysis. So I think I did this at the end of the last video. I'll redo it. For this system, find all the error constants and steady state errors to unit, step, ramp, and parabola. It's unity feedback. There's nothing in this feedback gain other than 1. The forward path then will be the product of these two guys. That is this. We see this single pole at the origin, which means it's a type 1. So we go back to our table here, and we use this row. We're type 1, so we're in this row. And here's our error constants. It's going to be infinity, G naught evaluated at 0, and 0. And the steady state errors will be 0, this calculation of a non-zero constant, and infinity. So we just pretty much are copying from that row. Here's those constants. I just read them off. The only calculation we need to make is this 0. And that was, remember, remove this pole at the origin, evaluate the rest of S equals 0. So we get 5 times 1 over 2 times 3, or 5 over 6. And the formula said the error is 1 over that. So that's 6/5. That was calculating an error. What if we were told that we must keep the steady state error under some threshold? And say we put a gain somewhere in this forward path, either here or there, so that this is the new forward path gain or transfer function. All we did was add the k to what we had before. But now we want to solve for k so that our steady state error needs some specification. Well, it's type 1, and it says to a ramp. Type 1, so that's where we will get a non-zero constant for the error, steady state error. We need to calculate this G sub naught, which will just be 5 times k times 1 over 6. This error is 1 over that times whatever the amplitude of the ramp was. And we're specified to be under 10% of that amplitude. The amplitudes cancel. Solve for this k. It says you need a k greater than 12 to get that steady state error under 10%. This caution didn't really apply in this example, but we'll get to where it does apply later. Don't mix up. Make sure you're using the right transfer function. When it's unity feedback like this, and we're talking about steady state errors, your calculations are based on the forward path transfer function. In fact, the beauty of using that table is you don't have to calculate the entire closed loop transfer function. I'll give you an example of that in a minute as well. All right. What type of system is this? And what is its steady state error to a step input of A in speed? The input is still a unit step. Not a unit step, but a step input of A, even though it's called speed. Both the input and output are in terms of speed. Anyway, it's unity feedback. We see no poles at 0 at the origin, so it is a type 0 system. And what is its steady state error? Type 0, we are now using this row. Steady state error to a step is this, where this case of P equals that G naught at 0. Here's what's, in fact, here is that calculation from that table. Case of P equals G naught, which will be 100 over 4 times 6 or 25 over 6. I'll put this K in here. And it just amounts to steady state error will be 6/31 of whatever A was, or about a little less than 0.2. Now, what if in addition they asked for what's the peak overshoot in the system? So this was the part B of the problem. To do that, you do need the entire transfer function, closed loop transfer function. And we've done this kind of thing many videos ago. Entire closed loop transfer function, since it's unity feedback, will just be this numerator over this denominator plus that numerator. That's the simplified version when you've got unity feedback. This numerator, 100, over this denominator, s plus 4, s plus 6, plus that numerator. That turns out to be a scaled version of a prototype second-order system with complex roots. We can relate these numbers to our prototype system parameters. Omega sub n will be the square root of this guy. Q zeta omega n will be 10. Calculate zeta, and from zeta you calculate peak overshoot. Go to your formula sheet. You did that before. Just make sure you know which transfer function for which purpose. That brings us to our last example, where I repeat the same caution. Part A is determine K3 to keep the steady state error, or have it the steady state error be 1 centimeter for unit step of 1 meter. Meaning we need a 1% steady state error. A unit step. And then part B, with that gain, determine the other parameters so that you get a peak overshoot less than 10%. Notice that feedback-wise, from the output back to the input parameter, that's unity gain. This is unity feedback system. This is a unity feedback system. But the forward path contains this sort of inner loop here. And we need to calculate that inner loop transfer function, or gain, by the good old G over 1 plus GH formula. The G is this product, H is K3. That forward path gain, which is just K1, K2. Oh, divided by the product of the denominators plus the product of the numerators. The denominators are, there's only one denominator that counts, IS, and I is 25. There's the 25S, and then this is the product of all those numerators. K1, K2, 1, K3. I included this one before I should have done this. The inner loop stops there. Anyway, this part here is the inner loop transfer function. Then the forward loop transfer function is that with the same thing with the extra 1 over s. There's the inner loop, and you've got the extra 1 over s. That's the forward path gain, which is all we need to do the steady state error calculations. Single pole at the origin, so it's type 1. P sub naught will just be rid of this S, that is 0. You just get K1, K2 over K1, K2, K3, which is just 1 over K3. And the error is 1 over that, which is K3. And that was specified to be 1%. So that tells us what K3 needs to be. For that, we needed only the forward path gain, or transfer function. To do the peak overshoot part, We need the whole transfer function. This will be the forward path gain, and the feedback gain is just one. So we can just, it's just going to be this numerator over this denominator plus this numerator. And now we've got K3, it equals 0.01. That's that. It simplifies. It's another prototype second order system. We relate the parameters and we calculate peak overshoot from a formula sheet. And that tells us what the product K1, K2 is. That ends steady state errors, especially for Unity feedback system, and it ends module 4, time domain analysis. Next up, stability.